Okay, yeah, welcome back, everyone. So, um, the second part, I'm going to talk about AI alignment. And so there's kind of two parts. First, intent alignment and existential risk. So AI alignment is maybe like a term that a lot of you will not have heard before or might not know what exactly it means or what I'm referring to by it. Um, so in my mind, it really refers to three different things, which I've listed here. Oh, right, I almost forgot. So let's just back up all the way to here and say, first of all, I'm happy for you guys to interrupt with clarifying questions at any time. And second of all, I wanted to check before I even get started if anyone has come up with any questions they want to ask over the break.
Yeah, there's a question.
Did I see a hand, or that's just someone stretching? All right, yeah, so I'll go ahead, but feel free to jump. Oh, I do see a hand. Great.
I'm going over my data.
Sorry, I'm sitting in the room. So you briefly touched on like visual explanation, salience maps, but also on how to evaluate generally methods for understanding an AI system. And one of the things that we had in Excite was seeing whether a method helps humans predict the behavior of an AI system, which I thought was very interesting because like for salience maps, a lot of the evaluations focus more on does the human feel like they understood the system, which is like sort of a very different objective. And I feel like even within this like robustness and extendability research, often the optimal function is more sort of like fooling someone into thinking that they understood the system rather than actually developing something that we would call a genuine understanding. So I just wonder sort of like whether you could say a bit about that, about sort of like these predicting behavior versus like just asking people whether they understood the system and sort of what the research is on that moment.
Yeah. So very meta level comment. I found that really hard to hear. I don't know if there's anything we can do to improve the audio. I do think I still understood the the heart of your question though was when we're evaluating interpretability methods, it seems like maybe we should be more focused on like some operationalization about, is this helping the human make good predictions about the system's behavior as opposed to just giving them some feeling that they understand it? Is that, did I get it right?
Yes.
Great. Yeah, I basically 100% agree with that sentiment. I think that's one of my main like criticisms or sources of skepticism about the interpretability work that I've seen, and I have to admit I am not very up to date on it. Have never like looked into it that deeply, but it seems like a lot of it could just be a lot of just so stories to me, where it's just like, you know, oh yeah, it seems plausible, so like we'll say that that we're interpreting it. And I think this is, in my mind, this is sort of the heart of the problem. This is where one of the main challenges of interpretability lies, is just in getting a good methodology, a good operationalization to say like, actually, this is in doing a good job of interpreting the system. So the proposal of, does it help a human make predictions about the system's behavior? I think that's an interesting one. I think you have to be a little bit careful, or like there's some details there that are going to matter a lot. So like if I have the system itself can do a really good job of predicting how it's going to behave, but that won't really help me understand why it's behaving that way, right? So like when I've thought about this, and I'm sure other people have thought about it more and maybe have better proposals, but I thought maybe what you should do is sort of let the human study some interpretation of the model for a period of time and read it. And maybe even they can take notes or have access to some notes about it. And then they have to predict the behavior of the model based on that. So they don't have access to like a sort of arbitrary tool, which could, again, just be the model itself, but maybe a very limited description of the model's behavior. And that can be limited by just saying, look, it's going to be like 1 page of text, or 5 pages of text, or something like that. Or it could be limited by saying the human gets to like study this model for as long as they want using this interpretability tool, But then at the end of the day, we're going to take the tool away, and they're just going to have to make predictions about what the model would do in different situations without access to the tool or access to the model. So I don't know of any research that I can quote you that does either of those things. I think, maybe several years ago, there wasn't really much research doing any sort of human studies on interpretability methods, or not like putting serious efforts into it that I was aware of. But I think there has been some more serious effort to do that sort of thing since then. Yeah, I'm just not very up to date on it to say more than that, but I think it's a really good point. So thanks for mentioning it.
Thank you. There's a second question. Hi, can you hear me?
Yeah. Try to speak slowly and enunciate though, because the acoustics are just terrible for me, unfortunately.
Right. I've got a bit of a tangent on your predictive policing report. So there is currently research where robots are being used to put out forest fires, and the robots are being used to put out forest fires, and you do that using predictive reports of which parts of the forest are likely to catch fire. And I would assume that it's a natural extension that we do the same for crime and policing. The only difference is that the robots don't start the fires. So you would assume that AI safety is more about telling humans how to use AI safety. So what is it about AI where we try to think of safety which should be encoded in the system itself as opposed to something else like mechanical engineering safety or electrical engineering safety?
This time I couldn't hear well enough to understand the question, unfortunately. So you mentioned like the difference between predicting fires and predictive policing. So I think I caught that part, but then I didn't really catch the last part of the question.
Well, I just want to know what is it about AI safety as opposed to something else like mechanical engineering safety or electrical engineering safety. You just teach the people who apply it to apply it sensibly. So surely you would do the same with AI, or is it a fundamentally different problem?
Sorry, I still couldn't hear it well enough. Maybe it would help if somebody repeats it, like, I guess it's just the same mic, huh? But maybe you can try summarizing or something.
So what is the fundamental difference between AI safety and other safety measurements in other more traditional engineering disciplines, like mechanical engineering or electrical engineering, where you just teach the operator how to use the system rather than try to bake it into the system itself?
Got it. Yeah, so the difference between AI safety and engineering. Yeah, so it's a big question. Let's see. I guess so. I mean, I guess the stuff I'm going to talk about in this part of the talk is going to get at that to some extent. I think partially, like, I think it's important to like emphasize that this isn't like a purely technical problem. So there's a lot of the problem is about like having good design and development practices and like deploying things responsibly, and that includes just like sort of having best practices, but it might also include like looking at the incentive structures of developers and thinking about like governance of the technology. Generally speaking, I mean, I think one of the distinctive things about AI is like in general is that it has this very black box nature, and so we don't have like a very good scientific understanding of it, and I think it's also like quite complex in a lot of ways compared to other areas where we don't have like a detailed scientific understanding, but the tool or like the sort of behaviors are simple enough that we can still kind of get to a reasonable level of assurance using trial and error to understand what are best practices and doing safety testing. So I think there's like a lot that we can probably learn from traditional like engineering and engineering approaches to safety. But I think those are some of the distinctive aspects, is like the behavior is more complex and also in some sense more black box, although like we can see the parameters of the model, but that doesn't necessarily tell us much without good interpretability tools, and we don't really have a clear sense of like how to evaluate that those interpretability tools are good in the first place. At least I'm not aware of anyone having a good operationalization of that, sort of coming back to the previous question.
All right, thank you. There's no more questions, so feel free to move on.
Cool. All right. Yeah, thanks for the questions. Yeah, so I'm gonna have to like go pretty quickly through some of this. Yeah, so there are these three different like things that people sometimes mean by AI alignment. The first one is just like, how do we get the system to do what we want? The next one is, how do we get it to try to do what we want? And this is sort of a hand wavy thing at the moment. It's kind of anthropomorphizing the system a bit, but I think it does actually make sense to talk about it that way in a lot of contexts. That's what I call intent alignment. And so often when people are talking about alignment, they really have in mind intent alignment. The last thing that people mean by alignment is basically existential safety. So the community of people, that 100 or so researchers and other people in other areas who are working on trying to prevent AI from leading to premature human extinction or reduce the chance that that could happen. And these first two problems are just like purely technical problem, but this last one, AI existential safety, is definitely a socio-technical problem because it involves like governance and all sorts of stuff like that. So yeah, now we get to talk about the elephant in the room, which is really the Terminator in the room, which is this idea of existential safety, and like, isn't this just like crazy sci-fi stuff, which a lot of people have said, a lot of news articles have sort of said that. On the other hand, I think actually, if you look at, so there's sort of this impression that people have, I guess, that, AI researchers aren't really worried about this, or like the experts aren't, and this is just kind of people like, Elon Musk or Bill Gates, or these people who don't really know what they're talking about. But yeah, if you actually look at what, experts say, there's not actually that much disagreement, I don't think, in terms of like, if this is a potential problem and if there should be people working on it. So there's this blog, Slate Star Codex, that had a nice summary of it, I think, which is basically, there's this idea that there are skeptics and believers, but they basically believe the same thing. They just kind of emphasize different parts of it, like, oh, we shouldn't panic or ban AI research, but we should have people working on it, is the basic agreement. So yeah, people, when we talk about existential risk, so existential risk, maybe I didn't explain this. Existential risk is the risk of extinction, human extinction. And people have defined it in like slightly different ways, but that's the core of the idea. People like to talk about there being like sort of three different ways that this could happen, which is misuse, accidents, and then oftentimes people don't talk about this last one, which is unfortunate because I think it's the most important one, which is structural risk. And I think we should immediately be able to see that existential risk is something like a tragedy of the commons, because reducing existential risk, having a high level of existential safety, is a common good. We all benefit by lowering the probability that the world is going to end. But individually, we don't benefit that much by reducing that number by like 1 in a million. So a lot of people might be willing to take a 1 in a million chance of ending the world if it would mean that they are almost certain to become, a millionaire or a billionaire, or very powerful or popular or whatever. And if a lot of people were willing to take that trade and were offered that trade, then we'd have a lot of people, rolling that die over and over again, increasing the chance that the world would in fact end. So I have a few examples for the malicious use and accident. But yeah, I'll skip over them in the interest of time. So I think basically I don't really talk about misuse much because I think it's actually the least important. I think structural risk is by far the most important. But let's talk about like accident risk first, I guess. So the thing that I think, the main reason that I personally am worried about artificial intelligence posing existential risk to humanity is I'm worried about it getting out of control and us not being able to get it back in control. And you can imagine that happening like quite suddenly if AI systems suddenly became way smarter and more powerful than humans and just, there was some sort of sudden takeoff and takeover moment. More gradually. So for instance, if people are sort of gradually shut out of the economy, and then at some point we wake up and we notice that basically AI systems are running the show. They're running the companies, they're running the government. Maybe humans are like nominally involved at various points, but there's nobody who really has the power to sort of, switch it all off at some point. Sorry, I'm getting dry throat a bit. So why would this like happen, and why would it then lead to human extinction? So actually, let's skip to problem 2 in my list first. So instrumental goals. There's 3 problems that I think are, in my mind, make up the case for this. And I want to just explain what I think is the most compelling argument to me. I mean, other people have different arguments, but so instrumental goals. So this basically can be summarized as the ends justify the means. And I think this is pretty much implicit in the way that we build all AI systems today, in the sense that machine learning, I shouldn't say all AI systems, machine learning systems are driven by optimizing some metric. And really, we're just searching for whatever setting of the parameters happens to drive that metric up or down, depending if it's reward or loss. And yeah, so I think this is like really fairly innate to the way that we think about AI and rationality and rational agency more generally. And just to give examples of like what sort of things fall under instrumental goals, sorry, I should back up and say what instrumental goals are. Instrumental goals are things that are like broadly useful for achieving your terminal goal. So they are the ends, they're the means that are useful for a wide range of ends. And the ones that are most concerning are like basically acquiring power and resources. So the basic idea is like, no matter what your AI system is trying to do, let's say it's just trying to make a bunch of paper clips. This is the classic thought experiment. It just makes sense over the long term to like turn the whole world into paper clips. And to do that, you have to, take over the world, build a bunch of paperclip factories. Maybe you need to do some like research into or deep thought into how you're going to get away with this whole thing, because probably people are going to try and stop you. And then you have this instrumental goal of like disempowering people so that they can't stop you, et cetera, et cetera. And the argument is that this same kind of reasoning emerges when you're making these sort of long-term plans over open-ended spaces, sort of regardless of what the terminal goal is. So whether the goal is to like make paper clips or calculate a bunch of digits of pi, or like quote unquote make people happy or engaged or something, like however you operationalize these things, unless you sort of have captured human values perfectly or have captured human intentions perfectly, you're probably going to have these emergent instrumental goals that look like power seeking and including disempowering people so that they can't stop you from, doing whatever helps you achieve your goals in the long run. Yeah, so classic example of like an instrumental goal that is maybe not so threatening, or at least not in an obvious way, is like exploration versus exploitation in reinforcement learning. So in reinforcement learning, you want to get a lot of reward in the long term, but you will sacrifice your reward in the present in order to get more reward in the future. So similarly with like the paperclip thing, instead of making paperclips right now, maybe you can make a plan that's going to allow you to turn the whole world into paperclips in the long term, right? And so this is, like I said, a problem if we can't if we can't get our intentions across to the system robustly. And so the second piece of the puzzle is this thing called Goodhart's law, which is, or basically the difficulty of specifying exactly what we want, in code or using learning or code. And Goodhart's law basically says when a measure becomes a target, it ceases to be a good measure. So this isn't like some sort of mathematical law, it's just an adage, but I think, it holds true in a wide variety of circumstances and for a wide variety of reasons. So basically, we want to think of the AI system as something that is trying to do whatever we have literally asked it to do in the specification. And that might be, something that we just wrote down as like a reward function or loss function, might be something we learned. In any case, there's some objective that is some metric, and the AI system is just trying to optimize that metric. It's not trying to optimize for the spirit of the law, it's trying to optimize for the letter of the law, right? So we write down something and we had something else in mind, and unless what we wrote down is exactly what we had in mind, then the AI system is probably going to optimize for what we wrote down instead of what we actually wanted or intended. And we already encounter this problem in machine learning in various contexts. So we don't have like good metrics for translation. We have this blue score, and if you actually try and optimize the blue score, you kind of get garbage. So like even though blue score is actually a pretty good metric if you don't optimize against it, at least up to some point, once you start optimizing against it, it really ceases to be a good measure of translation quality. Another one that I think is really important and maybe gets into the more philosophical realm to some extent is like revealed preferences versus what I would call reflective preferences. So your revealed preferences is just whatever you happen to choose from the choices that are presented to you, whereas you don't always choose the thing that you sort of would like to choose if you were thinking carefully about it or if you were more enlightened. And you can see like recommender systems are often optimizing for like clicks or for sort of your immediate reaction. And so we get all of this clickbait instead of the things that would actually, add more value to our lives in the long run. So just to spell it out, if we put these two problems together, I've argued that like specifying what we want is difficult. Like difficult is maybe putting it too mildly. It seems basically intractable. Like we don't know a good way of doing this in general for things that are like complex goals about the real world. And because of this problem of instrumental goals, if we build goal-directed AI systems using something like reinforcement learning with a sufficiently large discount rate, those systems will in the limit, or at least if they learn to behave optimally, they will in fact seek power and influence over the world because that will help them optimize their goal. And again, their goal is not going to be what we actually want. It's going to be some proxy for what we want. And even if they realize that, oh, that isn't quite what we want, they're still going to want to optimize for it because that's how like goal-directed behavior works. And so they might resist attempts to change their goal or shut them down or otherwise interfere with their ability to achieve that goal. So if we think about combining those problems then with like AI systems becoming very advanced, very competent, more intelligent, more competent than humans, then we end up with out of control AI systems with goals that are different than ours, which I think is just pretty obviously something that would be dangerous. So you might say, like, why don't we only build AI systems that we're sure we can control so that they never get out of control and we never run into this kind of problem? And that's where we have to come back to this issue of structural risk. So I talked about this hypothetical situation where anyone can take like a 1 in a million chance of destroying the world, let's say, of building an out of control AI system that's going to destroy the world. And if they're willing to take that chance, they can benefit tremendously. They can, make billions of dollars. They can maybe outcompete their geopolitical rivals, etc. So I think this is really almost the core of the problem, more than any technical problem, is just this issue of structural risk where there's going to be strong incentives to not build the safest system that we can, but instead build one that's somewhat less safe, but more likely to enable us to defeat our rivals and enemies in various competitions. So, you know, here's just a very stylized example of the kind of trade-off that people might see. So you might have like option 1 is your safe AI system, and option 2 is your strong AI system. And the safe AI system maybe has all these nice properties, like there's a human in the loop, we can shut it down, it's very interpretable, we sort of have a sense of what it's actually doing, how it's making decisions, we've tested it a lot, and we're only deploying it in like some sort of narrow domain. So there's less risk of misbehavior, but it's also, all of these things are sort of limiting its capability to be as competitive as possible, you know, at something like, let's say, propaganda or cybersecurity. And so there's actually only like a 10% chance that we win, you know, whatever cybersecurity or propaganda or military or economic competition we're engaged in. On the other hand, we have option 2, which is the strong AI system. And this one can operate faster than humans, so we can't have a human in the loop anymore. It's just a giant, you know, black box neural net, let's say. It's maybe using the cutting, you know, state-of-the-art, cutting-edge algorithms that are not understood, but sure do a great job on all the benchmarks. And because we want to make sure that it's, you know, has access to all of the information that it could need to make the best strategic decisions in every situation, we've connected it to the internet and to the whole, you know, Internet of Things, to basically everything we can get our hands on, to give it, you know, access to more sensors and actuators. And so now we have a much better chance of winning these competitions, but at the same chance, we have more risk of misbehavior because it's not as well understood or tested, and we have much less ability to interfere if the system does start to misbehave because it's operating, you know, at such a quick speed, and it's it can do things that we might not even notice because it's plugged into so many different things. We won't even necessarily notice if it starts misbehaving. It might be able to get away with doing things covertly. So the general picture here, I think, is that there's going to be some sort of safety performance trade-off where you get more performance by giving AI, building a system that has more autonomy, but that also makes it less safe because it means that, you know, it has more control, basically. And I gave some, you know, stylized examples where maybe the safest thing you can build is just a paperweight, and then at the extreme end of performance, you have some sort of meta-learned, like self-modifying reinforcement learning agent with a good model of the world plugged into all sort of safe sensors and actuators. And the concern is that we might see a race to the bottom along this axis, where actors are sort of forced due to structural incentives to trade off safety more and more in order to get more and more performance, or else they just get out-competed. And, you know, just another example of the kind of like autonomy that autonomy giving more power to AI systems in some sense is deep learning, where we sort of said, hey, let's not have humans make the features, let's just have the system learn the features. And you can imagine in the future we're going to have the system like, you know, learn the learning algorithm, for instance, as well. And so this is sort of why I think this approach of capability control, which I mentioned a few slides back, like just making sure that we can keep the AI system under control, is not as promising as motivation control, basically trying to make sure that the system has the right intentions. And I still think that, you know, which I've also called intent alignment, I still think this one is really hard, and because of things like Goodhart's law, but it currently seems more promising to me. And I think it also seems more likely to scale. Because as your system gets smarter, it's more likely to find ways to, you know, to operate outside of the intended domain and to subvert different safeguards you have. Now, it won't necessarily have the incentive to do that. Like if you build a supervised learning system instead of a reinforcement learning system, maybe it just doesn't have any incentive whatsoever to influence the outside world. And it's just, you know, entirely myopic. We might come back to that a little bit later in the talk if I still have time. So yeah, instead of the Terminator, we should think of this as a problem maybe more like climate change, where even if we knew what the problem was and what the trade-offs were, it doesn't mean that we would actually, you know, as a species or as a civilization, a global, you know, society, make the right decision about those trade-offs. Cool. Yeah. So recapping the argument, I'll skip over it for time. I just want to mention that like this is just the argument that I find most compelling. There are other arguments, as I mentioned earlier. So like sort of the common sense argument from Jeff Hinton of like, well, controlling something that's smarter than you, that just seems hard. Stuart Russell, who's a big proponent of AI safety and alignment, likes to talk about this as the gorilla problem, where like gorillas kind of aren't running the show anymore. They sort of exist at the will of humans. If we encroach on their habitat or just decide on some day that we have a gorilla vendetta, then gorillas might very quickly cease to exist. And if we build AI systems that are smarter than us, then we will just be in a very similar situation to gorillas today. So it just kind of, obviously for that reason, seems tenuous and troubling. All of this, I don't expect to be like super convincing, and all of a sudden, you know, if you came into this talk thinking this is all bullshit, all of a sudden you're converted. But I do think that like reasonable people, if they think about this, should be able to agree that like this risk is non-negligible, we can do things to reduce it, and it's actually an ethical priority to work on that. And I'm not saying like, you know, AGI is imminent or that this is the most important problem. A lot of people who work on this might believe those things, but I don't think that it's that important for people to believe that. I think we should just all agree on these first three things, and that's what's important. So I want to say a little bit about what I think are distinctive aspects of aligning advanced AI systems. So all of the stuff that I talked about in the last session, specification, robustness, assurance, all of those problems are going to show up, you know, for systems that are advanced, you know, superhuman in various ways, maybe in all sorts of strategically relevant ways. But there are also maybe some problems that are sort of unique to thinking about the kind of systems that are, you know, super intelligent or superhuman, or at least just significantly more advanced than the ones that we have today. So this is an incomplete list, but the first one, so I already talked about like instrumental goals and power seeking. And, you know, instrumental goals are quite universal in a sense. They will crop up, you know, in any reinforcement learning setting if they're like just as a natural consequence of the way that reinforcement learners reason. They will think about, you know, delaying gratification and doing things that will help them achieve their long-term goal of, you know, maximizing returns better. But the instrumental goal of seeking power in particular, I think, is, you know, quite unlikely to arise until you have a sufficiently advanced, intelligent, open-ended system. And so I don't think we've seen any convincing examples of that so far. I think there are maybe like some toy examples that people have come up with, but nothing in the real world yet. But, you know, one of the examples of that would be like disabling an off switch. So even if we say, you know, a lot of people, when they hear about the idea of out of control AI, they're like, well, let's just have an off switch and then we'll turn it off, you know, problem solved. But if you have a power seeking intelligent AI system, it might find clever ways of disabling that off switch, which might look, you know, as simple as like cutting the wire. It might look more subtle, like distracting or manipulating people who might be throwing the off switch at crucial moments. You know, it could also just coerce people if it had the means, like blackmail or threaten violence against people if they, you know, threaten to turn it off. And a particular form of instrumental goal that I'll talk about a little bit more on the next slide is deception. So this could include like hiding its true intentions, or so, you know, if we had a system that like looked like it might want to disable its off switch, as soon as we notice that, we might say, oh, wow, that would be really bad. We should turn it off right away before it actually starts to try and do that. And so if you, as the AI system, started to think about, hey, you know, at some point I might want to disable my off switch, then it's natural to then think, oh, I better make sure that the humans don't find out about that, because then they'll definitely just turn me off. And so you naturally get this incentive to deceive humans as well. Another distinctive thing about advanced AI systems is recursive self-improvement. So a lot of people have argued, or in the AI alignment safety community, believe that AI systems might at some point get good at doing AI research, and at that point they might very quickly go from basically very quickly improve their capabilities because they can do more AI research, get better at doing AI research, and you have this feedback loop, which could lead to some sort of like sudden takeoff. And so this, you might expect this to happen like around human level AI if you just abstract away all of the nuance and say intelligence is just a scalar value. Then humans seem decent at doing AI research. Imagine if we could automate that and do it like a million times faster, because computers are so much faster than humans. Then we might make progress a lot faster, and so on and so forth. And there's already some of that happening in some sense, right? I mean, with humans in the loop, like we build better AI tools, sometimes using AI for like hyperparameter search, or I don't know, I'm sure somebody has like used codecs to write AI code and stuff like this. But so far, I don't think we've seen any like major gains from this so far. And I think that's because it actually requires a high degree of intelligence to get a significant feedback loop going here. But it certainly seems plausible at some point that that could happen. I think it's very speculative, however. Finally, there's this issue of wireheading. So wireheading is basically hijacking the reward signal. And I have a photo of a lab rat or mouse, I'm not sure, that is being wireheaded. So this is actually an experiment that you can do where you implant some sort of diode or whatever, sorry, I forget the term, a wire basically into the head of the rat, into some area of its brain, and then pushing this lever will stimulate that area of the brain. And if you put it in the right place, somewhere that causes some sort of pleasure or compulsive behavior on the part of the animal, it will literally just self-stimulate until it dies. So it will not stop to eat or drink or sleep or anything. And of course, that doesn't sound very dangerous if you think about it that way, but that's because animals are not like all that rational, and AI systems, on the other hand, are sort of built according to some sort of principles of rationality usually. And so if they were able to get access to their own reward signal, would not self-stimulate until they die necessarily. They might instead build a large edifice to protect their ability to self-stimulate and maximize the reward that way. Again, going back to the instrumental goals argument. And so that's a concern specifically because kind of no matter what reward signal you give an agent, there's always a really good way of optimizing the reward, which is just to hack into the computer, like get control of the hardware where the reward is being calculated or stored, and just directly set the value in the reward memory register to some maximal value. And I don't know if that's exactly the form that we should expect that kind of behavior to take if it does in fact happen in practice. But it just gives you a flavor of this concern, which is that you want to make your reward function be something about the external world, but ultimately it gets computed by like sensors and memory registers of a computer. And so what's to say that the AI system won't just directly manipulate those instead of manipulating the external world to stimulate them? Yeah, so just to say a little bit more about this deception thing. Let's see, how much time do I have? Nope, I'm skipping it. All right. Actually, I'm going to take 1 minute here because I need more water. I'll be right back. All right, sorry about that. Thanks for bearing with me. Now's probably a good time to pause and ask if anyone has any quick questions.
Yeah, there's a question. Thank you very much. That's all. Can you hear me? Can you hear me?
Yes.
Yes. I was just wondering whether the AI safety and alignment they do actually share the same objectives in the sense where the categories or the definition of these two as well true if the incentive of the AI tools that you're building is for greater good. However, if we apply these two words to applications such as warfare and firearm, where people are using AI to develop a more intelligent weapons, then yes, alignment holds true if your tool is targeting the right people to harm the right people. However, it doesn't hold true for safety in a sense that yes, under control, you are harming the right people, but once it's out of control, you are harming your own ally. Then is that something that it comes down to the user's political point of view of how they would benefit from the tools that they are developing, and hence it just comes down to the application issues where how you use such things.
Yeah, great question. So I think like I guess I'll try and pick apart two parts of the question. The first part I think is just like aren't these things very different? So I said like alignment means these different things, and you're saying, well, these are actually really different, and I basically agree with that. So I think yeah, it is just maybe somewhat unfortunate that these kind of get blurred together in the way that the term is currently used. So in particular, I think solving these technical problems, as I mentioned, is not actually sufficient for solving the socio-technical problem. And we can see that by just recognizing that it's not a purely technical problem. So the example you gave is a good one, where it's not just a matter of like having the alignment technique, it's also making sure that people then, are responsible in the way that they develop and use the systems. But I'll say a couple things sort of to support the idea that technical alignment work is actually a good way to increase existential safety. And I think I would say like I am less of this opinion than most people in this community. So I think a lot of people in this community view this as largely a technical problem, and I think that is a mistake. On the other hand, I think if we're not able to solve this technical problem, then I think it's very hard to imagine that we can develop AI like responsibly and not actually have a significant risk from developing more and more advanced AI systems. So I think, and that's because of sort of this, the first two parts of the argument, the instrumental goals and Goodhart's law. So if we don't have like a good technical solution to that part of the problem, then I think we won't be able to align the systems with anybody. But I think people are still going to build them, and so to some extent, it's like if we have a system that is unable to be controlled, we're in a better position than if we just aren't able to control the thing in the first place. Then we just have to make sure that the right people are in control, and that makes it more like every other technology where like people like to say technology is just a tool, it can be used for good or bad, and I think there's a lot of truth in that. It's less true for AI than other technologies, unfortunately. And I think like good technical alignment work could make it more true. there's also this argument that even the sort of more social parts of this problem, so like, yeah, like preventing misuse and sort of coordinating to make sure that the technology is developed responsibly, also would benefit from applying, a very intelligent, aligned AI to work on those problems. So if you imagine that we actually have, AI systems that are smarter than people, they might be able to do a better job of like developing good governance structures and systems than people are, and that might help us address problems like misuse or some of the other aspects of like structural risk and creating good incentives. Yeah, thanks for the question. All right, so I will go back and try and take a few minutes to tell you a little bit about some of my work on specification failures, because I want to give you a flavor. In the first part, I sort of gave you a flavor of some of the areas of research that are relevant to safety, and I am really specifically trying to work on like safety and alignment, and so I want to explain, some of the stuff that I think is exciting and that I've worked on, motivated by that. So I've talked about like intent alignment, and I think specification, this is sort of naturally viewed as a specification problem in my mind, where it's hard to specify the right thing. If we could specify the right thing, then the AI system would probably have that goal. Like we can basically just set the goal if we're doing reinforcement learning. Is at least that's a naive gloss on the way this works. And so reward modeling, I mentioned in the first half, is this framework and paradigm that a lot of people are working on, but for the most part, they're working on either just like improving techniques for learning reward functions or applying it to do things like align large language models. And I'm more interested in understanding, like, is this whole paradigm and framework useful and how can it fail? So I'm going to try and tell you a little bit about these three works. So the first two are done with some of my students and other collaborators since I started as a professor, and the last one is something I did during my PhD. So the first of these is defining and characterizing reward gaming. So Goodhart's law basically says that you're always going to get reward gaming. So whenever you specify a proxy instead of the actual true thing that you want, if you optimize that proxy, you're not going to get the kind of behavior you want. And in reinforcement learning, we refer to that as reward gaming or reward hacking. So I already showed you this example of the boat race. Here's another example from another paper in Atari. And what you see here in green is the returns according to a learned reward model. And in red, you see the actual ground truth score. So here we're pretending that we don't have the score in order to evaluate how well the learned reward actually tracks the true reward. And what we find is that up to some certain number of time steps, they're actually tracking each other quite well, at least for Hero and Montezuma's Revenge. Like there's a strong correlation between the model reward and the ground truth reward. But then at some point that suddenly switches. And so by optimizing this proxy too hard, we end up with something that scores really well according to the proxy, but scores really poorly according to the ground truth reward. And this is reward gaming, or it's also sometimes called reward hacking. And in our paper, we define what it means for two reward functions to be gameable. So is it possible that by optimizing this proxy, we would end up with reward gaming is the question that we ask in this paper. And in order to do that, first we define what it means to be gameable. And basically we just say, look, we're going to model optimization as just some arbitrary sequence of policies. And then if at some point, by moving from pi to pi prime, we could increase our reward according to the proxy, while simultaneously decreasing our reward according to the true reward function. Sorry, I should be saying returns instead of rewards. Then that could lead to gaming, because then, optimizing the proxy would say, oh yeah, pi prime is better. And so we would switch to using policy pi prime. but that would at the same time lead us to actually do worse according to the ground truth reward function. And I think in the interest of time, I'm gonna like basically skip over the details of the results, but what we find is pretty interesting to me. We find that ungameability is basically impossible if you're considering the set of all policies. So this is only, there's no non-trivial relationship of ungameability. So you might think that there are proxies that are actually like reasonable proxies, and you can optimize that proxy and be guaranteed that you won't mess up the true reward. But it turns out that's basically impossible, at least according to the assumptions we made in the way that we formalized this problem. And so in order to like get anywhere, we need to restrict the policy set and say we're not going to consider every possible policy. Maybe we're only going to consider like deterministic policies. So we're considering finite MDPs, so there's only finitely many deterministic policies. Once we do that, there's always some ungameable pair of reward functions. So like not all hope is lost. But yeah, so that's kind of like the quick summary of the results. I won't try and walk through the proofs here, but I will say, like, in terms of the sort of the conclusions that we draw in terms of implications for alignment, one thing is that this idea of optimizing proxy rewards is maybe actually not a good one. And it turns out that we might need a very good proxy, and in fact, in our case, the proxy needs to be like perfect in order to guarantee that we won't have any reward gaming. On the other hand, we know that this approach is successful in practice a lot of times of reward modeling. So maybe it's fine to do reward modeling so long as we view it as just a way of learning a policy and we don't take the reward function that we learn too seriously. So we shouldn't think of optimization as like something, we shouldn't actually think of like, oh, we really want to optimize the reward function. We should think of optimization as a process or a heuristic. And that's sort of, in line with like how we usually think about training in machine learning. We want to avoid overfitting. And so we should sort of take that same mentality to reinforcement learning. Next paper I want to talk to you about is this paper, which was just accepted at ICML with my student Laura and all these other collaborators. So basically the point here is that when you fail out of distribution in a reinforcement learning context, you can basically fail in one of two ways. You can have an agent that just can't do anything meaningful in this new context, or you can have one that actually is still capable of doing some sort of goal-directed behavior, but is pursuing the wrong goal. And so there's a simple example here that I think does a great job of illustrating this, which is this coin run environment. And the goal here is for the agent to run to the end of the level and get the coin that's at the end of the level. And in fact, we say that the goal is to get the coin. And it just so happens that the coin is always at the end of the level during training. So what's going to happen at test time when the coin is somewhere else? And the answer is that the agent just goes to the end of the level anyways and ignores the coin. And this is because the coin and end of level were perfectly correlated, or in some of our experiments, not quite perfectly correlated, but highly correlated during training. And so the agent wasn't really able to determine, is it the coin that gives me the reward, or is it the end of the level that gives me the reward? And in this case, it generalized to say it's the end of the level, and then it was competently pursuing the wrong goal off distribution. And this is particularly concerning because of all of the issues of goal-directed behavior, like instrumental goals that we mentioned earlier. And it kind of shows an even more sort of, what would you call it, insidious failure mode than misspecification, because in this case, the goal that we specified was actually correct. It was, rewarded for getting to the coin. The issue was just that the training data wasn't diverse enough for it to understand that that was the goal and learn to generalize that goal appropriately. Yep. And so this last paper, I'm again just going to give a really quick gloss on, and I'm going to start by jumping all the way here to talking about the different sources of specification failure. So I've told you that we can have a specification failure where the agent has the wrong intentions if we just give it the wrong reward function. And that was sort of the point of this first paper on reward gaming. The second paper was saying, look, even if we give it the right reward function, it can still fail because it can generalize that reward function inappropriately. So when we're only giving it feedback of rewards and we're not giving it the reward function in closed form, it has to implicitly learn a reward function. And it's not always going to be unambiguous what the reward was based on the training data, what the reward function was, I should say. And so even if we have the perfect reward function, which is probably never going to happen in practice, but we might have one that we think is really good, it still doesn't mean that it's going to generalize that correctly, because it might learn its own internal representation of a different reward function. So this final work is complicating the situation even a bit more and saying, look, we don't just have to think about the reward function. The behavior that the agent chooses is not defined only by the reward, but also by other aspects of how we set up the learning problem. And in particular, we can think about this in terms of these paths of influence. So here I have this example of like content recommendation, and the goal, let's say, is to maximize the user clicking on things. And you want to do that by matching the content to the user's interests, right? So if your goal is to get the content and the user's interest to match, you might think the best way of doing that is to change the content so that it aligns with the user's interests. But of course, if the content that you show the user also changes their interests, then you might be able to get these things to match by changing the user's interests in some deliberate way instead of by changing the content. And this is generally, I think, undesirable. What we want is we want to only change the content to match the user and not the other way around. But that doesn't come across in a reward function or a loss function that just says these two things should match. So what we have to do is we have to think about which paths of influence the agent is optimizing over. So here, what the agent recommends might influence the user in the future, as well as influencing whether or not they click in the present. And that ability to influence the user in the future is an aspect of reality, but we don't want the agent to optimize over that. And so what we need is a way of saying, yes, optimize the crate even in the future, right? We want to do some sort of exploration to learn what the user wants, but don't optimize it by trying to influence the user. So basically act as if these paths of influence didn't exist, even though they do. Yeah, so I think I'm out of time, so I will leave it there. Thanks for all of your attention. Oh, I remind you that I'm looking for postdocs, and the deadline is quite soon. If you're interested, please get in touch. And I'd be happy to take some questions, although I know I'm over time, so I'll leave it to the organizers and the audience to determine if we'll take any more questions right now. Thanks again.
Any questions? Thank you, David. There are no more questions.
All right. Thanks, everyone.
Bye.